When we picture structural failure, we usually imagine something being crushed. If you place a heavy concrete block under a hydraulic press and push hard enough, the sheer compressive force eventually shatters the material. Swap that block out for something tall and slender and apply that exact same downward pressure. The material never gets close to crushing. Instead, under a tiny fraction of the load that broke the concrete, the slender object suddenly and silently bows sideways. The failure is purely geometric. Even while the internal structure of the material remains far below its breaking point, the shape itself can no longer maintain its vertical alignment. Engineers call this sudden loss of structural stability buckling. It strikes instantly, without warning, at weight loads far lower than the raw material is actually capable of supporting. To calculate when this lateral collapse will happen, we have to look closely at columns. In structural engineering, a column's entire job is to take a heavy compressive force from above and transfer it straight down to the ground. Engineering columns are defined by their relative proportions. While a short, thick block will eventually crush under load, a true column is long and slender enough to introduce the risk of lateral failure. The standard rule of thumb is slenderness. If an object's unsupported length is roughly 10 times greater than its narrowest width, it behaves like a column. The moment a structure stretches past that physical threshold, its rules of survival change entirely. The threat shifts from crushing to buckling. To prevent collapse, structural engineers have to pinpoint the exact mathematical moment buckling begins. They look for a specific number known as the critical load. This is the invisible boundary separating a solid building from a disaster. Below the critical load, the column stays straight in stable equilibrium. Reach the critical threshold, and it enters neutral equilibrium, bowing slightly on a knife's edge. Push a fraction over that limit. Unstable equilibrium takes over, and it buckles entirely. Calculating this precise tipping point is a mandatory step in designing any structure taller than a few stories. In 1757, the mathematician Leonhard Euler wrote the formula that predicts this exact moment of failure. The capacity of a column begins with the top of Euler's equation, the inherent stiffness of the material being used. But stiffness alone isn't enough. Euler also factored in the cross-section, specifically how efficiently the shape of the column resists bending in any given direction. A solid steel rod wastes heavy material near its center, doing little to prevent bending. Hollow tubes and wide flange H-sections push mass to the edges, maximizing rigidity while saving weight. But the denominator of the equation holds the real danger. It relies on the overall unsupported length. And that length variable is strictly squared. Because of that exponent, doubling a column's height doesn't cut its load-carrying capacity in half. It drops the capacity down to a quarter. Every time a building reaches higher into the sky, the mathematical penalty for length multiplies, aggressively eating away at the strength of the steel. If length destroys strength at an exponential rate, building vertical skyscrapers should be practically impossible. But engineers found a way to cheat Euler's formula. They manipulate how a column is anchored to the surrounding building, altering what is called its effective length. Take two identical steel columns. Pin the first one at the top and bottom so it can pivot, and it bends in a long, continuous C-curve. But take the second column and bolt it completely flat, fixed rigidly into the foundation and the ceiling. By physically preventing the extreme ends from rotating, the fixed column is forced into an S-curve under pressure. Only the middle half of the pillar is actually allowed to buckle. Having the effective length feeds back into Euler's squared denominator. Clamping the ends of the column physically quadruples its load capacity without using a single extra ounce of steel. The way a column is held at its ends directly determines its load-carrying capacity, making connection design as essential as the choice of cross-section. These principles of effective length govern the structural steel codes written to standardize modern global construction. Instead of relying entirely on rigid joints at top and bottom, modern skyscrapers use diagonal braces anchoring directly into the midpoint of vertical columns. Pinning the column exactly halfway up physically prevents the center from bowing outward. Like fixed ends, this cuts the unsupported length in half and quadruples the structural capacity. Add a second brace, locking the column down into thirds, and the total load capacity multiplies by 9. Precise bracing allows slender materials to carry loads that would otherwise require far heavier components. Calculated geometry provides the strength. By manipulating shapes, lengths, and rigid connections, we hold back the mathematics of collapse. Every skyline on Earth is a continuous victory over buckling.